Socratic Math Tutor here. Today we're going to solve this inequality, and we're supposed to express our answer using interval notation. So what that basically means is we need to take this inequality and we need to show it's equivalent to something of the form x in an interval here. So we need an explicit description of these numbers. These need to be explicitly given, or explicitly stated. Possibly we might have a union here, and we might have some further intervals out here. Okay, and obviously these numbers should also be given explicitly. So as long as we can find those intervals and those numbers, and as long as we can show that this is bidirectional, a bidirectional relationship, we'll get full marks and we'll get a big tick. The problem with the standard techniques given by your average maths teacher is that they don't give us the bidirectional relationship. So what they're going to give us is, we're going to start with this, and we're going to deduce some conclusions. So we're going to assume this is the standard approach. We're going to deduce some conclusions, and we'll find that x is in a particular interval. And then we'll say, okay, we're done. And depending on who's grading us, we might not get full marks for that, because if they actually understand how logic works, they'll want the backwards implication too. And the reason we need the backwards implication is because otherwise this interval might end up being too big. So for example, suppose our original condition is that, I don't know, x minus 1 is less than 5. And suppose we solve this to find that x is less than 6. Therefore, x is in negative infinity through to 6. Well, we can also conclude on the next step that x is in negative infinity through to 7. If we've assumed this, then we can conclude this, right? And so it is actually logically true that if x minus 1 is less than 5, then x is in this interval. That's logically true. But we've actually got too many solutions here. Okay, so the problem is that we didn't do this backwards implication, and in fact, if we actually started with if we started with this line and tried to prove this line, we wouldn't be able to prove it. Basically, we wouldn't be able to assume this and prove this because it's just not true, right? So that's kind of the big picture of what's wrong with the standard approach that your standard math teacher or even mathematician will show you. And so what I want to do is offer you guys a rigorous approach that actually just gets the job done. It works every time. I want to show you how this technique works, not on this problem, but rather on an easier problem. So we're going to look at 3x plus 2y equals 4. Let's call this A. Actually, let's call it A0. And we'll also look at 2x plus 3y equals 1. So these will be our simultaneous equations, and we'll call this B0. And I'll just show you how to solve these in a really rigorous way that gives you that bidirectional relationship. Then we'll apply the technique to solving this, okay? So the first step is to just pick the thing we want to manipulate. So I'm going to manipulate A0 to start with. So I'll write down A0, if and only if, and just for clarity, I'll just rewrite it here. You don't actually need to rewrite it in your first step. Then I'll start manipulating it. So I'm going to try and get y by itself. So 2y equals 4 minus 3x, which is equivalent to y equals a half 4 minus 3x. And then I go, and so here's the secret. Here, I want to go call this A1. So now I'll start manipulating B0. Okay, so B0 is equivalent to, well, I'll just write out the condition again. Once again, you can skip this step in your own workings, but just so you guys know what's going on, I'll just make that very clear. Now I'm going to replace y with this value here. Okay, so 3 times half 4 minus 3x. Okay. And we just want to emphasize that these two lines are only equivalent if A1 is true, if A1 is assumed, okay? And then we can keep going. But by the way, the important thing here is to only use the latest version of A. So I'm not allowed to use A0 here. I've always got to use the latest version of all my symbols. So if I'm up to A5, I'm not allowed to use A0 through to A4. I can only use A5, okay? Then I'll just keep going. Oh, I need an equals 1 here. So I'll expand this out, which is 2, okay? So we'll go ahead and call this B1. So let's go A1 is equivalent to, now this is what we started with, or this is what we defined A1 to be, let's say. So we'll go ahead and use that. So A1 is equivalent to y equals half 4 minus 3x. It's meant to be a 3. Which is equivalent to y equals half 4 minus 3 times 2. Okay. So 6. And I'll just put here if B1. Remember, we're allowed to use the latest version of B. So in this context, it would be B1. Which is equivalent to y equals -1. And so at this point, we're done, right? So what we've learned is that A0 and B0 is equivalent to the latest version of A, so A2, and the latest version of B, so that would be B1, which is equivalent to, firstly, this. So get that going, y equals -1, and this condition, right? Just into there. X equals 2. And so what we end up with is this bidirectional relationship between our original conditions and our final conditions. And so because of that, we can say at this point that the problem is completely solved. You know, full marks, 100% rigor. There's nothing more to do there. So that's how you solve simultaneous equations in a rigorous way that gets you both directions you need in one go. Okay, so now that we can solve simultaneous equations, let's go ahead and deploy those skills to give a genuinely rigorous solution to this problem, okay? So what we're gonna do is we're gonna call this whatever we want, call this P. So P is equivalent to, just for emphasis, I'll rewrite it. So 3 minus x is greater than the absolute value of x minus 4. We can rearrange that so we get 3 minus x on the left, absolute value of x minus 4 also on the left, greater than 1. And the reason we were able to move this over is because it's positive. And it turns out that whenever you have an inequality like this, if you multiply both sides by a positive number, the inequality remains true, and you don't need to switch the order or anything like that. On the other hand, if you were to multiply both sides by a negative number, it would switch. But in this case, that's not what we've done. And we need to put and here. And the reason is that there's an extra condition we need in here. So in particular, implicitly in this condition, there's an assumption that this denominator is not 0. It's not written explicitly, but implicitly we can say that the absolute value of x minus 4 is not allowed to be 0. So in other words, x minus 4 is not allowed to be 0. And so that becomes our extra assumption out here. X minus 4 is not 0. And that ensures that these two lines are in fact equivalent. Okay, now we can go ahead and use De Morgan's laws. So this in particular has two cases. So x minus 4 can be less than 0, or x minus 4 can be greater than 0. Let's just use De Morgan's laws to break the problem up. I'm going to write really small because this final line, well, this next line, let's say, is super long. So I'll rewrite this, and I'll put in our first condition, and x minus 4 is less than 0. Is the first part, or just using De Morgan's laws. Apologize for this super long line. You can avoid writing this really long line if you make some more definitions. But I think it's a bit clearer not to introduce any more notation. So there we've got a super long line. So P is equivalent to this condition. And that's really good because we've got two cases. That's the OR. And each of these cases, well, they're combined. They involve AND, right? So basically this is simultaneous. It's not simultaneous equations, but it's simultaneous conditions. And so that technique we just saw is applicable here, right? So what we're going to do, we're going to call this A naught, call this B naught, call this B naught. We'll go ahead and call this C naught, call this C naught, and we'll call this D naught. Call this D naught. Okay? And so what we're going to do is we're going to solve these two conditions simultaneously because they're combined with AND. And we'll solve these two conditions simultaneously because they're combined with AND. Then we'll just put that together and that will get us P. So I'm going to start off by looking at this. So let's start off with A naught. It's equivalent to, just for the sake of completeness, I'll reiterate what A naught is. It's that. It's this greater than 1. And then I can replace absolute value of x minus 4 with 4 minus x. And that's because we're going to assume B naught for that equivalence, right? Which, because we're assuming that x minus 4 is less than 0, therefore the absolute value of x minus 4 is the negative of x minus 4, which is 4 minus x, okay? Let's go ahead and expand this out. Well, actually, no, I want to negate both these brackets just to put things in a more familiar form. It's a general rule, if you put things in a familiar form, you're less likely to make mistakes. So for that previous line, I just negated both those brackets. There we are. And let's get all the parts of the quadratic on one side of our inequality. So let's go ahead and call this A1 in line with our simultaneous conditions technique. It's also a good idea just to call this something so we can talk about this polynomial. I'll go ahead and call this P. You could call it P or Q. It's polynomial, it's quadratic, whatever you want to call it. We can compute the discriminant of P pretty easily. So it's B squared minus 4 times A times C, which will be 49 minus 44, which is 5. And what that tells us is that the graph of P will actually cross the x-axis, right? So it's going to look something like this. It's going to cross the x-axis in 2 points, and that's simply because the discriminant of P is positive. If the discriminant was negative, it would be kind of sitting up here. It wouldn't be crossing at all. And if it was 0, it would be touching but not crossing, okay? So those are some basic facts you should know about discriminants. Because it's positive, we can say that it's actually going to cross. And so we can actually look at this condition of this polynomial being greater than 0, and we can see on our graph what values of x will actually make that true, right? So we can see that out here, the corresponding y value will be positive, and out here the corresponding y value will be positive, whereas between the two solutions, the corresponding y value is negative. So this condition is equivalent to saying that we're left of the smaller of the two roots, or we're right of the larger of the two. Hopefully that's clear enough. If you don't find that very satisfying, I've also got a theorem here that you can have a look at that kind of explains that in more detail. In practice, the way you work out a theorem like that is by just drawing a graph and then doing maybe a little bit of math to just prove to yourself that the graph hasn't misled you in some way. So if you do prefer formulae, feel free to use this formula. I'm not going to talk it out in any more detail than just putting it up, because I think the graphical method's pretty good. But if you really like formulae, just pause now, stare at it, read it, compare it with the graph, and you know, maybe that'll help you. But I'm not gonna talk about that formula any further. So on that basis, we conclude that A1 is equivalent to the statement that x is less than the smaller of the two roots. So the smaller of the two roots is this. Okay, that comes from the quadratic formula. It's negative b minus the square root of delta over 2a. Or x is greater than the larger of the two roots. So 7 plus the square root of delta over 2a. Okay, so these are really coming from the quadratic formula. They're also in that previous theorem that I just showed you guys. However you want to remember them, make sure you have a technique, either the quadratic formula or the theorem I showed you, okay? So let's go ahead and call this E2. Now I just want to spend a moment comparing these numbers with the number in this condition, right? So if we rearrange this condition, we get x is less than 4. And so I want to compare this number with 4 and this number with 4, and I want to find out which of them is bigger. And the reason is because we're trying to intersect this condition with this one, and so to know the intersection of this interval with these two intervals, we need to know kind of how they relate to each other, you know, how they lie on the real line with respect to each other. Let's get rid of all that rubbish. So let's just hypothesize that 4 is less than this number. So the smaller of the two roots. I'm not saying it's true, I'm just hypothesizing it. So we can rearrange that to this, which we can rearrange to this. And this is just clearly not true. The statement 1 is less than negative 5 is false. So this was untrue, which means actually 4 is the larger of the two. Okay, so 4 is either somewhere between these two, it's either in the middle, or it's out here. So let's try and work out where it is. So again, I'll hypothesize that 4 is less than, this time the larger of the two roots. Just do a bit of working here. 8 is less than 7 plus root 5. 1 is less than root 5. And this is true, right? 1 is less than 5. So we can square both sides, and it becomes really clear that this is true. And so what that tells us is that 4 is somewhere between this solution and that solution. So at this point, we're basically done with this case. And so to finish off the problem, we just write A0 and B0 is equivalent to A2 and B0, which is equivalent to x is less than 7 minus root 5 over 2. That's the smaller of the two roots. Or x is greater than 7 plus root 5 over 2. And x minus 4 is less than 0. And based on the computations we did here, we can say this is equivalent to just saying that x is less than 7 minus root 5 over 2. So if you're a bit unsure about why this is equivalent to that, in light of these computations, try drawing this out. Just draw a copy of the real line and draw your 4 conditions. Keep in mind which numbers are bigger than which out of these 3 numbers, which of them are bigger based on these computations, and you'll see how we're able to conclude this. And just to put our answer in interval notation like it asks, we should rewrite this as x in negative infinity. Wow, that is a crazy infinity sign. Even more crazy than the concept of infinity. Okay, negative infinity through to the smaller of the two roots. Okay, and so that's this condition. Now I'm going to leave it as an exercise for you to do the same kind of reasoning as this on this case. So once again, you need to do, the technique of simultaneous conditions. And what you're going to find is that this case is equivalent to false. So after the video's over, go ahead and try and finish it off, show that this is false. And once you've done that, you'll be able to see how this problem finishes, right? So we're trying to rewrite P using interval notation. Case 1 is the condition x in negative infinity through to 7 minus root 5 over 2. Case 2 is just not true. That can never happen. And so this is equivalent to x in negative infinity through to the smaller of those two roots. So that's a rigorous solution to this original problem we were looking at, to this problem. Just put it there. And so we conclude that this can be written using interval notation in this way. And that's the solution.